pakken met dubbelpunten. In het Engels.
Dank u wel.
Ik weet niet of het veel verschil is.
So I'd like to welcome you all to my masterpiece presentation today. I'm really happy to be back here and see so many familiar faces after such a long time. So as the title gives away, it's about nodal surfaces. What are nodal surfaces? Well, those are surfaces with nodes. What is a node? I'm going to tell you a bit. First of all, I'd like to mention, I would like to thank supervisors. I would like to thank Geert van Geer for allowing me to study in Lisbon last year. It's been an amazing experience. And really, it was really nice. And I'd like to thank Margarida Mendes Lopez, who was the supervisor in Lisbon. Of course, thanks to Bookland for being available in such short term. And Thesis for so much. So we're going to start. I would like to tell you, first I'm going to give you an overview of what we're going to talk about today. I'll introduce the main question. That is sort of the backbone of the whole thesis. I'll tell you a bit about the history of this question and then zoom in on the modern way to view this kind of problem. After that, oh wait a sec. The modern argument kind of splits up in two parts, which is geometrical, based on the notion of an even set of nodes. There's a combinatorial part based on coding theory, and of course there's the way how we can put them together, which is the third part. So after this, I will zoom in on two alternative ways of proving what you want to prove that we discussed in the thesis. And lastly, if there is time, I will tell something about what is not known yet in this certain area. So, what is the main question? First, I will have to tell you what our language will be, so we are talking about the same thing. We work in algebraic geometry. All varieties will be over the fixed page field, namely complex numbers. This allows us to work both in the algebraic category as in the real category, so we can equip our surfaces with the normal Euclidean topology and view it as a four-dimensional real manifold. So in this switch from complex to real numbers, we have a doubling of dimension. Now, a definition. I promised you already I would tell this. A node. Most of you should be familiar with the surface singularities, or singularities of varieties in general. A node is, in some sense, the most simple one. You can describe it most easily in the analytic category. So it looks locally like the affine column. Can give you a picture. Oh, I can't, there's no chalk. Here. It looks locally in holomorphic coordinates like this. And this is, of course, the singularity. Now, what are properties of a node that we'll use? Well, first, a node is resolved by single blow-up. For those who don't know what blow-up is, in general, you can resolve singularities of any algebraic variety by a process called blowing up. We don't need to know now what it is in general form. We know, we only need to know here that it suffices to blow up only the node once to obtain a smooth surface. So we will replace locally our surface, which looks like this, by this. And there's a map from this surface to this surface, which is an isomorphism almost everywhere, except at this exceptional curve, which is contracted to one point. What happens if you blow up a node? You get one so-called exceptional curve. It is smooth, it is rational. It's therefore isomorphic to the projected line, P1. And it has self-intersection -2. For the people unfamiliar to the notion of self-intersection, well, one can, of course, look at curves on a surface. One can count its intersection points. If one does so with multiplicity, one obtains a theory of intersection on a surface. There's one problem, however. If you want to calculate the intersection of the curve with itself, well, a priori, we think there's an infinite number of intersection points, which does not really make a lot of sense in the theory. But as it turns out, there's a canonical way to extend the theory. And through this extension, which is really natural, it will be possible for a curve to have a self-intersection which is finite, but it can also be negative. It's really weird intuitively, but it makes a lot of sense. I can't tell you why, but I hope you can trust this. Such a curve, having these properties in general, is called a nodal curve, and this is a theorem that any such curve, so a smooth rational curve on a surface with self-intersection -2, can be contracted in this sense to node. So the theory of nodes on a surface or nodal curves on a surface, they're completely equivalent. They're the same thing. Now, what is the main question? Let S be a surface in P3 of degree D. Then what is the maximum number of nodes on S? Turns out this depends on the degree, and therefore it's denoted mu of D. This is really classical notation. It's been used for at least 150 years, maybe more. Second part of the presentation, I promise you a little history. There's the older results. In 1863, the mathematician Schlafly classified all singular cubics in P3. And as a side result, of course, he knew the maximum number of nodes on a surface, which was 4. A year later, 1864, Commerce showed he did not classify all quartic surfaces. That was done in 1905, if I'm not mistaken, by Yesa. But he did find already that a quartic surface possesses at most 16 points. So there's no surface having more than 16, and there is a surface having 16 nodes. Quite a few years later, Togliatti, an Italian geometer, he constructed a quintic surface with 31 nodes. It was, however, at that time unknown if a quintic surface with more than 31 nodes existed. I decided to add some pictures. Here's the cubic surface admitting 4 nodes, known as the Cayley cubic. Here is the Kummer quartic. It was actually already known by Fresno and physicists, but it's a quartic surface having 16 nodes. And here lastly, the surface I just talked about is a quintic surface with 31 nodes, constructed by Togliatti. So what is the more modern viewpoint of this problem? It was actually introduced, it was a technique introduced by the French mathematician Arnaud Beaulieu. He's actually going to speak at the conference in algebraic geometry, which is in July in Amsterdam, which is really interesting. So in 1979, he introduced a new technique. I'll tell you later exactly what he did. But as a result, he found that no quintic surface with more than 31 nodes exists. The same technique, although way more difficult to apply in this case, was used in 1997 by Jaffe and Luberman to prove the following quality. The sextic surface has at most 65 nodes, and this bounds the fact that there is a sextic surface with 65 nodes. Up to now, there's been some new work, but it's been mainly improvements of existing proofs. Most notable point is that this proof uses computer calculations, which is somewhat not desirable, while the modern version of the proof, especially the parts written by Pignatelli and Tonoli, does not use computers at all. It's really nice. So, what did Beaulieu do? First, let us fix our notation. We have a singular surface, sigma, embedded in P3. And we assume it has a singularity of only nodes. That is, it's a nodal surface. One shows really easily that the number of nodes must be finite. So we can number them, P1 up to P mu. As I told you, we can resolve the singularities, that is, blow them up to a smooth surface S. We lose the embedding in P3, but that's not a problem. And each node corresponds to a single exceptional curve, a nodal curve. So we can number them E1 up to E mu in a natural way. What Beaulieu did was the following. He considered this map, which comes a bit out of the blue, but I can guide you in steps to it. So one can take the Fourier-Wheeling group generated on the exceptional, or that's the nodal curve, so that will be Z2 mu. One can map this to the Picard group of S, simply by sending the ith basis vector into the class of the ith nodal curve. Note that S is smooth. Now there's this theory, there's always a map from the Picard group to the second singular cohomology group, standard coefficients. This map need not be injected, but if this invariant of the surface vanishes, then it is injected. And what happens to be the case? This is always 0 for surfaces embedded in V3. The surface S shares the invariance of sigma. They have the same invariance. It's also a thing you can prove. So this holds, and this map is an injection. So we basically view the Picard group as being embedded in the second singular cohomology group. One thing that has to be noted is that S, when we use singular cohomology, it's a 4-dimensional real manifold. So don't be lured into thinking this is a dot cohomology group. We're going to need that later. So this map is basically this one, but reduced modulo 2. One can show also that the map going from this group to the same group but with coefficients modulo 2 is just reduction modulo 2. So we can get a nice diagram. And this is the map of the Euclid's phi. What happens? We're really interested in the kernel of this map. Why? Let us take the kernel elements. B. One can see, actually it's right here, that if we take a kernel element, we can look, it's basically a sequence of zeros and ones, right? So we can look at the coordinates where it's 1 and take exceptional curves, EI, exactly where the I coordinate of B is 1. It's a divisor. Because it's in its kernel, it's divisible by 2. In the sense that there is a divisor L in the Picard group of S such that 2L is congruent with the sum of the EI. Is this readable for everybody? So this is what it means to be divisible by 2. Why is it interesting? Well, let's take a look at the following definition / proposition. We pick a node, a set of nodes, the I indexed by uppercase I. The following will be equivalent. There exists a divisor L such that the sum of the divisors is congruent to 2L, that is, the sum of the divisors, sum of the exceptional curves is divisible by 2. That is equivalent to the existence of a double cover, that is surface X, and a finite map of degree 2, 2S, which is ramified exactly at the union of the exceptional curves. So the points that have only one pre-image are exactly the points in the exceptional curves, corresponding to the set of nodes you started with. This will come probably as no surprise. This is in turn equivalent to the existence of another double cover, but this time to the singular surface. Remember that this was the wall of this one, which is ramified exactly at the nodes, the same nodes you started with. If you are a bit confused by this, please ignore the next part. If you are not, please do not. But it's in turn equivalent to the existence of another surface, B in P3, which has contact with sigma. That is, if you take their product in a Chell ring, you get twice a curve. By definition, this means a contact along a curve. And this curve has a very special property. If you look at the nodes where it passes through, so the nodes of sigma, and you look at the nodes where it passes with odd multiplicity, that's exactly the set of nodes you started with. This means we also say that the set of nodes, Vi, is cut out through D by V. This is only going to matter throughout the end of the presentation again. But in any case, if such a condition holds, we call the set of nodes Vi even. Now let us get back to the last slide. This is stuff I already showed you just now. It's just a repetition. We had this remark. We looked at a kernel element. We saw it's equivalent to the sum of exceptional curves being divisible by 2. In our new terminology, this just means that the set of nodes, given by the coordinates of y, v that are 1, is even. This is nothing new. This is just a name for something. But our observation is now that this kernel is a vector space which captures a lot of geometric information about our surface sigma. Its kernels are in one correspondence with the even sets of nodes of sigma. Now, before I go on, I need to tell you about the second part. I told you there was a geometrical and a combinatorial part. Now, we'll do the second. A code is defined to be a subvector space of some kind, where F is always the field with two elements. And if we take an element of a code, its weight is defined as the number of its non-zero coordinates, or the number of the ones occurring in mathematical terms. It's written like this. This is notation for the weight. This is the number of non-zero coordinates. So getting back to the surface we were considering, the code we were considering, the kernel of phi, let's call it K from now on, is a code by definition. And what interpretation do we give to the weights of P? Well, we saw that the non-zero coordinates of P exactly told us which nodes were in the even set. So the cardinality of the nodes in this even set is exactly the weight by P. There's nothing special happening here. It's another name for the same thing. This is the geometric interpretation I just told you about. The weight of P is the cardinality of an even set of nodes. Now, we're going to put this together to arrive at our desired upper bound for mu. This is just a map again. I put it here just for reference. First observation. This group, what can we say about it? Well, you can use, actually it's not that hard. It's the universal coefficient theorem for cohomology and for correlativity. And it just rolls out that you take the second Petty number of S, and that's the dimension of a vector space over the field of two elements, and that's this group. So one knows that the image of phi has never a dimension bigger than the second Petty number of S. But we can do better. Namely, the code given by the image is totally isotropic. What does that mean? It means, well, I mentioned earlier this is the middle singular cohomology group. So we can consider the cut product on a cohomology group, and it restricts to this group. And what happens to be the case? Well, we embedded our Picard group in this group. We also have the intersection form on our Picard group. It's just counting intersections of curves with multiplicity. These happen to be the same. So, recalling that a nodal curve is a curve which intersects itself with multiplicity minus 2. Modulo 2, that's 0. Second thing, the nodal curves are disjoint. They don't intersect each other at all, just by definition. You can see it in the picture already. That means that each element in space spanned by the nodal curves is, if you take the inner product with another element, that will be 0. So by definition, the image code is totally isotropic. What do we know about totally isotropic codes? Well, the dimension is never bigger than half the dimension of the ambient space. So we are obtaining this inequality. There's half the dimension of the ambient space there. Using the standard dimension theorem from linear algebra, we obtain that our kernel, we call it K, has dimension at least mu minus half the second Bendy number of S. A really important interpretation of this is that if we fix the degree of S, one can show that the Bendy number only depends on the degree. And we let mu increase, so we just allow more and more nodes. At some point, this kernel will become non-trivial. And if we add nodes from that point on, it will increase in dimension. So when mu increases, the surface must possess more and more even sets of nodes. Why is this important? We're going to use the weights of the code K. Again, the geometrical part, there's very strong restrictions on the cardinality of even sets of nodes. For example, they always need to be divisible by 4. If the degree of the surface is even always need to be divisible by 8. That's a remark due to Miles Reed. On a quintic, there's actually the only possibilities are 16 and 20. So there's only 2. But they very much, that must be remarked, they very much depend on the degree of the surface. What happens to be the case in combinatorics, if a code is allowed very few weights, one can find strong bounds on its dimension, it's an upper bound. it makes sense. If you force the vectors to be of the same weight, but all their sums as well, they need to overlap in a really specific way, and one cannot allow the code to grow arbitrarily big. So let us find an upper bound for the dimension of k and call it u. Geometric implementation, once again, a surface of x degree cannot possess arbitrarily much even sets of nodes. I think most of you see it coming now. We saw that if mu increases, there must be more even sets of nodes. But if we keep the degree fixed, this amount of even set of nodes cannot grow too much. If we put it together, this is the first inequality we found. This is the second. And it's right there. We found an upper bound on mu. It's never bigger than this u. There it is, plus half the second Betty number of plus. This is Wolffiel's method. It's there's been quite some improvements in parts of the reasoning, but basically this is how the quintic case is dealt with even now. And the same method is applied in the sextet case. We considered pre-6 surfaces. And by the same reasoning, there's just a lot of more case distinctions, and it's quite harder actually. But it led to the result of Jaffe and Blumerman showing that a sextet cannot have more than 65 nodes. That's those two proofs is what we treat mainly in the thesis. There's some diversions, but that's the backbone. So now I told you what the thesis is about. Let me zoom in on the quintic case, because we were happy to find it's not necessarily an improvement, but we found another way to show the combinatoric part of Wolffiel's reasoning. So I need to give you the problem just as it is. There's no time to explain why we want this. But recall that we had our code K. There was a kernel of this map phi. We want, that's what we really want, the code K to be at most of dimension 5. This will allow us to prove that the mu of 5 is not more than 31. And we are given, again, this is just something I have to let you believe, the weights of K, that is cardinalities of even sets of nodes on a quintic surface, will be either 16 or 20. That's the only possibilities. So the weights of K are 16 and 20. Next thing, this is nothing more than just a trick. If we assume, heading for a contradiction, a quintic surface to exist with more than 31 nodes, we can just take 32, because there are at least 32, and we can work with them. So if we look at the code K, we can assume it lives in a space with dimension 32. What was the thing that revealed it? He wrote in his paper actually that the colleague depended him to this lemma. It was a well-known lemma in coding theory. It reads as follows. Let V be a code of dimension D, and it lives in a space of dimension n. And we assume all of its weights to be high. That is at least n over 2. Then we arrive at bounds on the dimension. But also the case where equality holds is completely classified. Then V will be equal to this code dd, where D should be a number, it's the dimension of the code. It's a well-known code in coding theory. Of course, here I didn't write what it is, but we don't really need that at this moment. What he did, I'm going to rush a bit, so I'm going to skip the details. But from this inequality, one immediately obtains in our case, because our weights are 16 and 20, and this n is 32. 32 divided by 2 is 16, so indeed the weights of the code we're dealing with are at least n over 2. From this we obtain that D is at most 6. But we wanted it to be at most 5, so we're not done yet. But if we then continue by assuming our code K to be of dimension 6, we will have an equality here. K should be equal to D5 in this case, but D5 is a code with weights 16 and 32. And that's not possible. 32 cannot occur. So we arrived at a contradiction, and indeed, as Wolffiel showed in his paper, we obtained that the dimension of K is at most 5. Then another method based on the reasoning of Pignatelli and Pinoli the second case is the following. If we have a code, dimension D, and length L, what is the length? I have to tell you now. So if you embed a code in an ambient space, you can imagine that if there's a coordinate of this Fn, for all vectors P are 0, and it's basically, it doesn't really carry information about the code. We might as well delete it and end up with the same code. If you do this to all the useless coordinates, you obtain a minimal such n such that the code embeds in it. That's called the length of the code. So it's kind of the amount of coordinates it needs to be embedded in space. If we assume, we didn't assume anything yet, we just gave names to the side. But if now we assume that it has only two weights, let's call this W1 and W2, then this inequality holds. Well, what's this polynomial? It's given as follows. One should see this as a polynomial with fixed W1 and W2, and L is the variable, so L is the length. It's a quadratic polynomial with a positive coefficient for its quadratic term, so it attains a minimum. And what happens, because this is a quadratic polynomial, one gets a parabola which is a function of the length. No. It's like this. And it's due to the 1 minus d, should always be above it. What happens if you plot this, or you make a table, one sees that the dimension can only be, well, you get it as an immediate result again that the dimension is at most 6, but that's not yet what we want. Turns out that the only possibility for the dimension to be 6 is when the length is either 35 or 36. But because, as I showed you on the other slide, we can assume K to be embedded in a space with dimension 32. In particular, its length will be at most 32. It will never be 35 or 36. So again, we obtain that the dimension